Today we're going to start with some of those basic concepts of physics. Now I know most of the time when we hear the word physics, it sends most of us running for the hills. But in biology we have to get a little bit of the basic concepts in our heads so that we can understand how and why biological systems do what they do. We can understand how they're able to maintain homeostasis, how they're able to have all of those processes happen. So we have previously looked at some of those basic chemistry concepts. We looked at the structure of an atom, and when we looked at the structure of an atom, we really focused on that outer electron shell. And the reason why is because the electrons are going to determine whether or not that atom wants to bond. So remember, if we have an unfilled outer electron shell, our atom is more likely to make bonds. If we have a filled outer electron shell, our atom is more stable and less likely to make bonds. And biology is all about making bonds and breaking bonds. So that's why we had to get to the level of the atomic structure and really focus in on those electrons and then focus in on those bonds. The hydrogen weaker bonds, the ionic bonds where we have an atom giving up an electron in the relationship in that bond and another atom taking it in, and then the covalent bonds where we have that sharing of electrons. And specifically we focused on water. Remember, water is 2 hydrogens and an oxygen. We have that unequal sharing of electrons in the covalent bond between the hydrogen and the oxygen. The hydrogen's electrons spend more time hanging around the oxygen nucleus, which made the oxygen side of our water molecule more negative, and the hydrogen side more positive because the electron was spending more time down hanging around the oxygen atom in our water molecule. So we had to get those basics underneath our belt and really understand them, because now we're going to get into the more complicated, more challenging concepts of understanding all the processes happening inside of the cell. Now this is where we get to talk about energy. And I love talking about energy. Energy in its simplest definition, a definition that all disciplines can agree on, whether we're in engineering or whether we're in chemistry or biology. Energy is the capacity to do work. Now, one of the things I often talk about in biology is the idea that biological systems are lazy. They want to get the most amount of work done with the least amount of effort. So if we focus on that theme, if we focus on that concept, that biological systems are trying to get the most amount of work done without using any energy, then we can really get a good understanding of all of the processes happening inside of our cell. Now we've covered the parts of the cell, which is good because we're going to take that for granted when we start to talk about how the different organelles and the different components inside of the cell start to react. So let's come back to that concept of energy, the capacity to do work, and keep in mind our theme that biological systems are lazy and they want to get the most amount of work done with the least amount of effort. So we have previously covered the definition of simple diffusion, and we are manipulating simple diffusion all the time. We just haven't ever thought about it that way. We haven't woken up and thought, you know what? I need to manipulate simple diffusion right now. So remember, simple diffusion is a movement of any molecule from an area of high concentration to low concentration using no energy. So essentially what we have is we have a situation, if you imagine a concert like the K-pop concert. All the fans are waiting outside and they are crushed together and they really want to get in. We got a high concentration of humans outside of the concert, low concentration inside. All we got to do is open that door and whoosh! All of our humans move from an area of high concentration to low concentration. Now in the case of simple diffusion, our molecules will move from high to low concentration using no energy. We want to focus on that aspect of no energy. We start to look at cells and start to look at biological systems. So why are molecules going to do this? Why are they going to move from high to low concentration using no energy? Well, it's because of Brownian motion. If you have ever been around small children, kittens or puppies, they are constantly moving, wiggling and jiggling, wiggling and jiggling and moving until they fall asleep. So if we think about small children, puppies, and kittens as being like molecules, molecules are constantly moving and wiggling and jiggling, moving and wiggling and jiggling, and they're never going to sit still. They're constantly moving. Remember that picture of the atom and the electron shell, which was a three-dimensional trying to show that the electron was constantly moving, our entire atom, our entire molecule is wiggling and jiggling and wiggling and jiggling, and that's what we call Brownian motion. So because molecules were constantly moving and wiggling and jiggling, they're always going to want to move from an area of high concentration to low concentration. It's kind of like molecules were practicing social distancing before humans were. So I've got two examples here that I want to talk about to help us to connect with simple diffusion, because it is such a crucial concept in biology. So whenever we burn a candle, we have a high concentration of molecules right where that flame is volatilizing and making those molecules airborne. These molecules are going to move from an area of high concentration to low concentration until they spread throughout the entire room or throughout the entire house. So, high concentration here near the candle, low concentration through the room, and eventually all of those molecules will move from this area of high concentration to low concentration, making this room smell a lot better. Now let's say you're getting ready for a night out on the town. You put a little perfume or cologne on your neck. You have a high concentration of smelly molecules here close to your body. Low concentration of those molecules out through the room. Those molecules will diffuse. They will move from an area of high concentration to low concentration using no energy. And what you're hoping is that the person you're attracted to will follow that concentration gradient back to its source where it's a lot stronger, and both you and that person will have a much more enjoyable evening. The other way that we manipulate simple diffusion, but we don't think about it when we're doing it, is when we fart. When you fart, you have a very high concentration of stinky molecules close to you, low concentration in the room. Those molecules will move from an area of high concentration to low concentration using simple diffusion until everybody in the room is left with the same question: who dealt it? Now, we spend a lot of time on simple diffusion because biological systems are lazy, because they want to get the most amount of work done with the least amount of effort. So then we look to our cells, we look to our biological systems to see where they are using and manipulating simple diffusion. Another way that cells are going to move things in and out will be active transport. Remember, active transport requires energy, and we don't want to use active transport until we absolutely have to. So when cells are moving things back and forth across the plasma membrane, and they're using active transport, they're generally doing that in situations where they really need to control what gets in and what gets out. So when a cell is controlling the amount of glucose, that monosaccharide for carbohydrates, when it's controlling how much of that glucose it brings in, then it will be using pump protein, it will be using ATP energy. It's making that really refined control interaction with the environment. If cells are using simple diffusion, like letting oxygen and carbon dioxide come and go as they please, then a cell doesn't have control over those molecules coming and going. They're just going to come and go and come and go, and the cell's like, whatever, simple diffusion. I need you to come and go as you please. I don't want to be in control of this. But other things like glucose and sodium and potassium ions, our cells do need to control. If you're heading into the medical field, you're going to talk a lot about the sodium-potassium pump, controlling how those ions come and go in and out of a cell. That's part of how we control the neuron signaling, that electrical signal that goes from one neuron to the next. So when we are looking at movement in and out of a cell, we look for simple diffusion, we look for active transport, and again, we look for facilitated diffusion and some of those bulk movements like endocytosis and exocytosis. But today I want to shift gears a little bit and focus back in on the water molecule. Now we know that water is necessary for life. We've already covered some of those properties of water, specifically focusing in on the idea that water can break bonds and act as a solvent. So water is going to be important for a cell. Cell being our smallest unit of life. A cell is going to need a lot of water. Remember our solute to water ratio, our cell is about 99.9% water and just 0.1% stuff or solute. Those carbohydrates, proteins, lipids, nucleic acids, ions like potassium and sodium and chlorine. So most of our cell is going to be water. Our cell has that specialized aquaporin that uses facilitated diffusion, manipulating the polarity of water to move water faster than simple diffusion alone. When water is moving, we call that osmosis. When we're looking at osmosis, what we're going to do is we want to first make sure we're comparing two solutions. So generally that's going to be the solution inside of a cell and the solution outside of a cell, because cells do need to be surrounded in water. We're next going to look at the solute to water ratio. So when we're looking for water to move, we're looking for two main things. We're looking for water to move according to simple diffusion from an area of high concentration to low concentration. And we're looking for water to move because water is a solvent. Water is going to move from an area of low solute to an area of high solute. Water wants to be where the solute is. It wants to be where the stuff is. We have a classic experiment that we do to show the power of water moving because of simple diffusion, and more importantly, water moving because water is a solvent. It wants to be where the solute is. It wants to be where the stuff is. And that classic experiment is taking some kind of tube and then plunging it into a beaker of water. So I first want to start by drawing our beaker of water. So here's my beaker. And inside of my beaker, I've got some water. I'm going to draw some little waves. Now, this beaker has a solute to water ratio. I have 0% solute and 100% water. So inside of my beaker in this experiment, my solute to water ratio, 0% solute, 100% water. Into this beaker of water, I am going to drop my tube. So this is my tube, and in my tube, I have some kind of solution. I'm going to dye my solution green just so that I can have that kind of color difference. Now down here near the base of my tube, I have a semi-permeable membrane. Semi-permeable meaning that only certain stuff can get through. In this case, the only thing that can get through the membrane will be water. All the other molecules in my solution here, in my green solution, all those other molecules are going to stay put. They're going to be stuck inside of this green tube. So my green solution inside of my tube is going to have a solute to water ratio as well. That solute to water ratio is going to be 5% solute and it's going to be 95% water. Now, whenever we're calculating a solute to water ratio, remember our percentages always have to add up to 100%. We have to account for 100% of our solution. So, outside of my beaker, I have a solute to water ratio. Inside of my beaker, I have a solute to water ratio. Now, what's fun about this experiment is that we can get water to look like it's defying gravity. We can get the solution inside of our tube to start to rise upwards against gravity. And the way how that's going to happen is by manipulating the properties of water. So water is going to want to move from an area of high concentration outside of our beaker to lower concentration inside of our green tube. So it's going to move from 100% to the 95%. We have another reason why water is going to want to move. Water is attracted to stuff. It's attracted to where the solute is. It's like a shopaholic. It wants to be where all the stuff is. So, we have no stuff outside in our beaker. In our green tube, we have some solute. We have some stuff. So water is going to move from the 0% solute to the 5% solute inside of the tube. We have two reasons why water is going to rush in and start to force that liquid up through our tube. Looks like a magic trick, and it's just manipulating the properties of water. So the next thing to do is we want to be able to communicate this. And this is where we get into the terms for communicating our solute to water ratio. So when we have more solute and less water, we're going to use the term hypertonic. So when we look at our green tube, we have more solute, less water when comparing it to the beaker. So our green tube is going to have a hypertonic solution. When we look to our green tube, we have less solute and more water. So we're going to use that term hypotonic. To refer to the solution in the beaker. Now, one thing I want to point out is when we're using these terms, hypertonic or hypotonic, we are always comparing two solutions. In other words, the terms don't make sense unless we're labeling and talking about both solutions, because it is a term referring to the comparison. So, if we call one solution hyper, then the other solution by necessity has to be hypo. They can't both be hypertonic because then they would be isotonic. Isotonic means that we have the same solute to water ratio in one solution when compared to the other. In other words, both of our solutions have the exact same amount or percentage of solute, the exact same percentage of water. So keep that in mind when you're looking through the pictures, when you're reading about this in textbooks and you're watching videos. The assumption, the implication is that we're always comparing those two solutions. Now, me personally, when I was learning this, it was a lot easier for my brain to just focus on the stuff. Wherever there's more stuff, that's when I know I have the term hyper. Hyper means more than, it means excessive. So if I have more solute, that percentage is higher, then I can use my term hypertonic. If my percentage is lower, I can use my term hypotonic. If I have less solute, then I use hypotonic. There is less than. That's what hypo means. It's below, it's less than. So for me, focusing on the percentage solute helped me to use the terms, because the terms really are focusing on or assigning value and communicating about the solute. Now, implied in that is the percentage of water, that second part of our ratio. As you use these terms more, I think what you'll find is that your brain will start to be able to incorporate that second aspect. So you'll think hypertonic. Your brain will go more solute. And eventually your brain will start to fill in the second part of that definition, less water. Now, some of you out there have water brains, and it actually makes a lot more sense to focus on the percentage of water. And with hyper, you've got less water, and hypo, you've got more water, and that we're moving from high to low concentration. If you have that kind of brain and it works for you, stick with it. But what I have found is that for most of us, because the terms are referring to the solute, it's easier for us to focus on the solute first when we're learning about using and applying these terms. So this brings me to the homework. With the homework assignment, you are going to be looking at 2 case studies. Now, these are real people that I worked with. I used to work with adults who have developmental issues. And both of these individuals were regularly hospitalized for the symptoms and symptoms that you will be reading about in the homework assignment. Now, my key tip to you when you're doing the homework assignment is first figure out which way water moved. If water is moving into a cell, then inside you have to have more solute. If you say the inside has more solute, then the outside has to have less solute. If water is moving out of a cell, then outside of the cell you have more solute. Water is attracted to all that stuff outside. If you call the outside, say that the outside has more solute, then inside has to have less solute. So focus on which way water is moving. Once you figured out which way water is going to move, then you assign the terms, knowing that water is attracted to stuff, and our terms are referring to which solution has more solute, has more stuff. Now, I do find that this is one of the more complicated topics, more challenging ones to learn. So give yourself extra time, practice this. I know it seems weird to maybe make coffee and think about, whether you're creating a hypertonic or hypotonic solution, or, I know it feels weird to deal with these things, but try to apply it to your life. Try to use these terms in ways that make sense, that will help you to remember and will drive home the concept. As always, you know how to get a hold of me. Please, please, please let me know if you have any questions.